A single exploding star can briefly outshine an entire galaxy. In this video you'll get the complete story of supernovae, what makes a star suddenly blow up, the different ways they die, and why those explosions are responsible for the iron in your blood, the calcium in your bones, and the gold on your finger. Picture a star running out of fuel and either collapsing inward or being pushed over the edge, then spraying its innards across space like the universe's most dramatic recycling program, with fireworks. First I'll walk you through every step in plain language, with everyday analogies, real observations, and a few surprising twists about how these blasts shaped planets, life, and even how we measure cosmic distances. Stick around and you'll leave able to explain supernovae to anyone, impress friends at parties, and see how a star's final act made our world possible, loud, bright, and oddly beautiful. A star's quiet life, from birth to main sequence. Stars begin life inside vast, cold clouds of gas and dust that float between the stars. These clouds are often called molecular clouds, which simply means they are cold enough for atoms to pair up into molecules, mostly hydrogen, and the whole thing can be compared to a fog bank in space. Small regions inside the cloud can become denser than their surroundings, and when that happens gravity takes over and starts pulling material inward. Picture a small snowball rolling down a hill and gathering more snow as it goes. That is how a young star grows heavier and denser. As the material falls inward it heats up and a compact, glowing ball called a protostar forms at the center. Surrounding that baby star is usually a flat, spinning sheet of leftover gas and dust known as an accretion disk. The disk behaves a lot like water spiraling down a drain, though far less messy. Some of these protostars blow out fast, narrow streams of gas along their poles. Those jets clear away surrounding material and can look dramatic in telescope pictures. During this phase most of the light the object gives off is infrared light, which is heat you can't see with your eyes but can detect with special instruments. Inside the contracting core the temperature keeps rising until it becomes hot enough for hydrogen atoms to fuse into helium, a process called nuclear fusion that releases a tremendous amount of energy. To explain fusion simply, when light atoms merge into slightly heavier ones, some mass turns into energy, and that energy is what makes a star shine. This is the same trick the sun uses every day. Once the outward pressure from fusion balances the inward pull of gravity, the star settles into a long-lasting steady state, often called the main sequence. The sun is a familiar example of a main sequence star. Think of it like a pressure cooker that has reached a steady whistle, steady, not static. Main sequence stars spend the bulk of their stable lives burning hydrogen in their cores, and the star's mass largely decides how bright and how hot it will be. More massive stars ignite fusion sooner, burn hotter and brighter, and use up their fuel faster, like a bonfire that flares brilliantly and then quickly dies down, while low-mass stars burn gently for a very long time, more like a tiny, steadfast candle. Young stars also influence their surroundings. The leftover disks around protostars are the raw material for planets, and stellar winds and jets sculpt nearby material in ways that help or hinder planet formation. In short, the quiet transition from a cold cloud to a steady burning main sequence star is a process of gathering, heating, balancing, and finally shining, an everyday cosmic routine that gives us the light we see in the night sky. When stars near the end, aging and instability. A star spends most of its life quietly turning hydrogen into helium in its central region, and that steady burning is what keeps it shining and stable. As the central fuel runs low the balance between outward pressure from that burning and inward pull of gravity shifts, and the star responds by changing shape and behavior. In everyday terms, think of a campfire that used to roar when you fed it logs but later only smolders. The way it smolders can be calm or suddenly sputter, depending on what's left and how the air moves around it. The core contracts and heats up while the outer layers may balloon outward, and those moving parts are where aging first shows itself. Lower mass stars behave differently from very massive ones. Small and medium stars swell into cool, bloated giants with bright, bloated envelopes. Picture a soufflé that puffs up as it cooks, while the inner regions work in thinner shells like layers of an onion. Those shells burn different fuels in sequence, one after another, and sometimes a shell will flare up suddenly, driving waves through the star. These shell flashes are like occasional sneezes from the star, short-lived but powerful enough to toss off surface material. The lost gas drifts away, forming a glowing cloud around the dead core, a bit like steam rising off a hot dish and catching the kitchen light. Massive stars take a more dramatic route because their centers can fuse progressively heavier elements, forming a layered, onion-like structure with different burning zones stacked inside. When fusion progresses to elements that no longer release energy when mashed together, the core can no longer push outward, and instability grows. It's comparable to trying to squeeze juice from a dried fruit. At some point squeezing harder doesn't help and the structure gives way. That rapid loss of support lets gravity take over and the core collapses inward, a violent change compared with the gentle shedding of lighter stars. Throughout late life a star shows many kinds of wobble and unrest. Some stars pulsate rhythmically, expanding and contracting like a breathing organism, which makes their brightness vary up and down. Others develop violent, irregular outflows where strong stellar winds peel away mass over long periods. Think of a hairdryer steadily blowing lightweight bits off a pile of leaves. Convection, hot material rising and cooler material sinking, can become chaotic in the bloated outer layers and drive localized eruptions, a bit like boiling water that suddenly spatters. All of these instabilities are part of the aging process, and they determine whether a star dies quietly by fading away or ends with a far louder finale. The physics of collapse, gravity versus pressure. At the heart of a massive star, the inward pull of gravity is constantly fighting an outward push from pressure, and that quiet balancing act is what keeps the star from simply collapsing on itself. Pressure here means several things: particles bouncing around because they are hot, thermal pressure, light itself pushing out, radiation pressure, and more exotic quantum effects that kick in when particles are packed so tightly they have no free room left, degeneracy pressure. Think of it like a crowded party. As long as people keep moving and pushing outward, the room holds. Stop the music and everyone slumps inward. Stars rely on the music, energy produced by fusion, until they cannot anymore. Fusion in the core provides thermal pressure by turning mass into energy and keeping particles agitated. Photons generated in that process create radiation pressure by exerting tiny kicks as they leave. Radiation pressure can be surprisingly real. Solar sails, which are thin sheets pushed by sunlight, use the same principle on a tiny scale. But fusion has a limit. Once the core builds up iron, further fusion consumes energy instead of releasing it, so the engine that stirs particles and makes pressure drops away. When the heat source fades, the balance tips toward gravity, and the core begins to compress. At first, crushing the core raises its temperature and density, and another kind of pressure appears because of quantum rules. Electrons refuse to be squeezed into the exact same state, so they create electron degeneracy pressure. To picture this, imagine passengers on a bus who insist on their own seat. Crowding more people on the bus won't make them share one seat. If the core's mass is below a certain threshold, about 1.4 times the mass of the Sun, that electron pressure can halt collapse and the star settles into a dense, cooling ember called a white dwarf. Short sentence. If the core is heavier than that limit, no amount of electron stubbornness will stop gravity. When gravity overwhelms electrons, the pressure cooker gets more extreme. Electrons get forced into protons, producing neutrons and releasing neutrinos in the process, and neutron degeneracy pressure steps up as the new line of defense. A neutron star is essentially a gigantic atomic nucleus where neutrons provide support in the same, one seat per particle, way. But if the core's mass is too great even for neutron degeneracy, meaning gravity is stronger than any particle's refusal to overlap, collapse continues until a black hole forms, a region where not even light escapes. Along the way, the rapid inrush can produce a rebounding shock and a flood of neutrinos. Those neutrinos can dump energy into the outer layers and help blow the star apart, which is the violent display we call a supernova. A crunchy end, and also oddly poetic. Core collapse supernovae, the death of massive stars. Massive stars that are many times heavier than the Sun end their lives in a violent collapse and explosion when their cores run out of fuel. Inside these giants, the nuclear furnace builds ever heavier elements by fusing lighter ones, hydrogen into helium, helium into carbon, and so on, until iron accumulates at the center. Fusion of iron doesn't release energy the way lighter element fusion does, so the star loses its steady outward pressure that balanced gravity. Without that pressure, the core succumbs to gravity and falls inward very rapidly. This sudden inward fall is like a cosmic pressure cooker whose steam valve has failed. The core compresses until protons and electrons are forced together into neutrons, and enormous densities are reached. The collapse halts when the neutrons are packed so tightly that they push back. This creates a rebound and launches a shock wave outward. That shock is what helps rip the star apart, blowing off the outer layers in a brilliant display. Think of it like knocking out the bottom block of a Jenga tower. The top suddenly drops and the pieces scatter. Tiny particles called neutrinos play a starring role even though they are almost invisible. These ghost-like particles carry away most of the energy released during collapse, streaming through matter almost as if it weren't there. Yet a small fraction deposit energy behind the shock and help revive it, allowing the star's envelope to be hurled into space. In practical terms, neutrinos are to a supernova what the steam is to an exploding boiler, mostly unseen, but absolutely crucial to the drama. When the outer layers are expelled, what remains is a compact core that can be one of two things depending on how massive it is. If the core is stopped by the pressure of neutrons, it becomes a neutron star, an object with more mass than the Sun squeezed into a sphere roughly the size of a small city. If the core is heavier still, gravity wins entirely and a black hole forms, an object whose gravity prevents even light from escaping. Both outcomes are extreme compared to anything we see on Earth, but they are the natural results of how matter behaves under crushing pressure. The explosion itself lights up the star's surroundings and seeds the galaxy with elements forged during the star's life and in the explosion. Layers that once made silicon, oxygen, and iron are flung outward and mix into the interstellar gas, later becoming parts of new stars, planets, and even the ingredients for life. You can think of a supernova like a cosmic compost pile. It breaks down the old and spreads the material that new things will grow from, though on a scale that makes backyard compost look tiny. Observationally, these events are both bright and varied. They can outshine entire galaxies for a short time and leave behind expanding clouds called supernova remnants that glow in radio and 10th-ray light. Astronomers use the light curves and spectra, the changing brightness and the fingerprints of elements in the light, to understand how the explosion happened and what the star was like before it died. It's a bit like forensic science on a cosmic scale. The scattered clues tell the story of the star's last moments and its contribution to the universe. Thermonuclear supernovae, white dwarfs that explode. White dwarfs are the dense leftovers of ordinary stars. Think of a sun-like star squished down to the size of a planet. They are extremely compact, so compact that a spoonful of their material would weigh like a truck, and they are held up not by heat but by a quirky quantum rule that acts like an invisible crowd control. Because of that rule, when the center starts to heat and nuclear reactions try to switch on, the usual safety valve of expansion is missing, and that can let a small spark turn into a savage fire. This is the basic setup for a thermonuclear supernova, the kind astronomers often call a type Ia, a white dwarf suddenly turning its stored fuel into an enormous blast of light and debris. There are two main ways a white dwarf can reach the point of eruption. In one, it has a companion star and slowly siphons matter from it, like a roommate sneaking snacks until the pantry is bare. The added material increases pressure and temperature in the core until carbon fusion begins uncontrollably. In the other scenario, two white dwarfs orbit each other and eventually collide or merge. The shock and compression from that union can also kick off runaway fusion. Both paths lead to the same dramatic end. Fusion spreads through the star in a fraction of a minute to a few minutes, turning light elements into heavier ones and releasing more energy than the star had stored. The explosion itself is a thermonuclear runaway, which means the fusion reactions feed on their own heat and race through the star without the stabilizing effect of expansion. The entire white dwarf is typically ripped apart. Nothing dense remains behind. Ejecta fly outward at blistering speeds, tens of thousands of kilometers per hour per second, or more simply, far faster than anything on Earth moves, carrying newly made elements into space. Among those products is nickel-56, which decays into cobalt and then iron, and those decay steps pump energy into the expanding gases, causing the supernova to shine brightly for weeks. That radioactive glow is why some of these explosions can outshine entire galaxies for a short time. Astronomers read light from these events to learn what happened. Spectra, light split into its ingredient colors, act like fingerprints, showing which elements are present. Thermonuclear supernovae typically lack hydrogen fingerprints, and they show signs of intermediate mass and iron group elements instead. Because many of them reach a similar peak brightness, they have been used as distance markers across the universe. Think of them as reliably bright beacons on a foggy night, though with some personal quirks that astronomers are still learning to correct for. There is active debate about which progenitor path dominates, and recent observations have found examples of both accreting systems and mergers, so nature might use more than one route to produce nearly the same result. Beyond spectacular light shows, these explosions seed space with iron and other heavy elements that later become part of planets, rocks, and even the iron in our blood. In that sense, thermonuclear supernovae are both cosmic demolition events and cosmic recycling plants. They also provide important checks on our measurements of the universe, so understanding exactly how they ignite and explode is a bit like figuring out why a row of identical light bulbs sometimes flicker differently, crucial for precise work. And while the physics sounds intimidating, the core idea is simple: a star that has been packed down so tightly that heat can't stop the fire, and when fusion finally wins, the star is spectacularly unmade. Light and spectra, what supernovae reveal. Light from a supernova carries direct clues about what exploded, how fast the debris is moving, and what elements were made in the blast. When astronomers split that light into a rainbow, a spectrum, they read patterns that work like chemical fingerprints. Simple tools such as a glass prism do the same thing in a classroom, spreading white light into colors. A supernova's spectrum does that, plus reveals the atoms hiding in the glow. Dark lines and bright lines in the spectrum tell different stories. Dark lines happen when atoms in the expanding gas absorb specific colors, leaving gaps. Bright lines appear when atoms emit light at particular colors. Think of an atom as a musical instrument, each one plays only certain notes. If you hear a trumpet note, you know a trumpet is present. If you see a hydrogen line in a supernova spectrum, you know hydrogen is present. That's how astronomers identify elements in explosions from light alone. The width and shift of those lines are also information-packed. When the gas is moving very fast, the lines get smeared out and broadened, indicating high speed. If the whole pattern shifts toward the blue or red, it means the material is moving toward us or away from us, thanks to the Doppler effect, the same effect that makes a passing ambulance siren change pitch. In supernovae, line broadening shows that debris can race outward at thousands to tens of thousands of kilometers per second, which is fast enough to cross a small country in an hour. How the brightness changes over time, the so-called light curve, pairs with spectral changes to reveal the engine behind the light. Some supernovae get bright quickly and then fade in a reproducible way. Their spectra show certain ions and a lack of hydrogen, which points to a specific origin. Other explosions begin with hydrogen-rich spectra and show a different fading pattern. Using light curves is a bit like watching a cooking show. The timing plus the smell gives you the recipe. Radioactive elements produced in the explosion power much of the light we see later on. Short-lived radioactive atoms decay and release particles that heat the gas, causing it to glow. By following the decline of brightness and tracking spectral lines that come from iron group elements, astronomers can infer how much radioactive material was made. It's similar to checking how many embers remain after a bonfire to estimate how hot it once burned. Spectra change as the supernova ages, revealing deeper layers over time. Early spectra sample the outer skin of the star, often hot and ionized, showing elements that were near the surface. Weeks to months later, the outer layers become thin and the spectrum shifts to emission from inner, heavier elements forged during the explosion. This gradual unveiling is like slicing through a layered cake and finding different fillings at each layer. Polarization and subtle shifts in the light can also hint at shape. Light that becomes polarized after scattering off dust or asymmetric ejecta suggests the explosion wasn't perfectly spherical. A little humor helps. Not every cosmic party is perfectly round. Observing polarization tells astronomers whether the blast was more like a smooth balloon pop or a lopsided fireworks burst. Light echoes give extra chances to study a past event. Sometimes light reflects off distant dust and arrives later, carrying an older version of the spectrum. That echo can let astronomers re-examine the early stages as if they had a time machine. It's like finding a voicemail of the beginning of the show when you missed the live broadcast. Putting all these clues together, line identities, widths, shifts, how brightness rises and falls, and polarization, astronomers build a detailed picture of the explosion, its composition, energy, geometry, and the processes powering the light. Everyday examples, such as prisms, sirens, and fireworks, make these ideas feel familiar, while precise spectral measurements turn a pretty light into a forensic toolkit for understanding stellar death. Neutrinos and the invisible messenger. When a massive star collapses under its own weight, an enormous flood of tiny particles is unleashed, and most of the star's energy slips away with them. These particles are called neutrinos. Think of them as nearly invisible messengers that hardly ever bump into anything. They stream out of the collapsing core in such numbers that they carry away almost all of the energy released, leaving only a sliver for the bright light show that follows. Neutrinos are born by simple, violent processes deep inside the star. Pressure so intense that electrons get squashed into protons turns some of those protons into neutrons, and each time that happens a neutrino is spit out. It's a bit like squeezing a tube of toothpaste and watching a tiny bead pop out. That bead flies away no matter what walls you build. Different ways of making neutrinos add up during collapse: thermal agitation, particle collisions, and those electron squeezes, so the core becomes a prolific neutrino factory. Because neutrinos interact so weakly with matter, they escape almost immediately, while light can be trapped for a long time inside the star's thick outer layers. That means neutrinos reach observers before the first visible flash, carrying direct news from the core. Detecting them is hard work. Detectors are basically giant pools of very pure water or massive blocks of Antarctic ice, watched for tiny flashes of light when a neutrino finally manages the rare feat of nudging an atomic particle. Those flashes are like the faint tick of a distant clock when everything else is roaring, rare, but extremely informative. Neutrinos also change their identity en route, which is both annoying and fascinating. They flip between types, so an instrument tuned to one kind might miss some of them. It's like trying to count birds that keep changing color mid-flight. Scientists use networks of detectors that complement each other, increasing the chance of catching the full story. When a neutrino interaction happens, the signal is brief and faint, but the pattern tells researchers about conditions that no light-based observation can reveal. The practical payoff is huge. These invisible messengers give a direct peek into the engine of the explosion and even help power it. A portion of the neutrino swarm deposits energy back into the surrounding material, helping to revive shock waves and fling the star's outer layers into space. They also influence how certain heavy elements are made during the blast. So although they're shy and slippery, neutrinos are central characters, the secret backstage crew that both reports on and nudges the grand finale of a dying star. A little spooky, yes, but also the universe's way of whispering its deepest secrets right into our most sensitive detectors. Shockwaves, remnants, and pulsar birthdays. When a massive star ends its life in a powerful explosion, a sharp front of pressure and heat races outward through space. This front, called a shockwave in plain terms, is like the sudden shove you feel from a passing sonic boom or the ripple that slaps your face when someone jumps into a calm pond. It compresses, heats, and speeds up the gas it meets. The gas caught by the shock can be heated to temperatures so high that atoms lose their electrons, turning the material into a glowing soup of charged particles. Bright light comes from this heated gas, and different parts glow at different colors of light and at radio and 10th ray wavelengths, depending on how hot and energetic they are. As the shockwave plows into surrounding gas and dust, it piles that material into a shell and creates what astronomers call a supernova remnant. Think of it like the expanding ring a pebble makes on a pond, except the ring is full of hot, glowing gas and the water is mostly invisible interstellar material. The interior of a remnant can stay very hot and tenuous, while the outer shell collects denser clumps into wispy filaments that look like taffy pulled by invisible hands. These filaments often contain heavy elements forged inside the star: iron, oxygen, silicon, which get stirred into the galaxy the way a compost heap returns nutrients to a garden, helping future stars and planets form with the raw ingredients for rocky worlds and even life. Shockwaves are also efficient particle accelerators. Charged particles bounce back and forth across the moving front and gain energy with each crossing, similar to how a tennis ball gains speed when hit repeatedly between players. Over time those particles reach extremely high energies and become what we detect as cosmic rays, tiny, fast-moving bits of matter that zoom through space and sometimes slam into Earth's atmosphere. The shock's interaction with magnetic fields makes electrons spiral and radiate, producing radio waves and tenth rays that we can detect with telescopes. These signals act like fingerprints, telling astronomers how strong the shock is and how it is changing the local space. A neutron star is often born in the heart of this chaos when the core of the exploded star collapses into an incredibly dense object. Picture a teaspoon of that material weighing as much as many mountains, dense enough to boggle the imagination, and spinning like a figure skater pulling in her arms. With rapid rotation and a strong magnetic field, the new neutron star can act like a cosmic lighthouse. Beams of radiation sweep out and appear as regular pulses to a distant observer. These pulsars are essentially newborns in astronomical terms, and their first breaths are powerful winds of energetic particles that carve out their own small nebula inside the larger supernova remnant. The interaction between a newly formed pulsar and the expanding remnant often creates a distinct glowing bubble called a pulsar wind nebula. This bubble can show rings, jets, and chaotic wisps, and it shines brightly in tenth rays and radio waves. A well-known example shows a central pulsar powering a bright, tangled nebula that looks like a pinwheel on high-energy photographs. If a pulsar gets a strong kick during the explosion, it can move away from the center, dragging its wind and leaving behind a trail, rather like a child running through falling confetti and leaving a glittery path. These processes are not just spectacular shows, they reshape their surroundings and influence how galaxies evolve. Supernova shockwaves compress nearby clouds and can trigger new rounds of star formation, or they can clear out cavities and stall the birth of stars. Pulsars act as precise, natural clocks that scientists use to test physics under extreme conditions, and their winds help mix and heat the interstellar medium. In short, shocks sweep, remnants decorate, and pulsars keep celebrating, sometimes loudly, always energetically, while they seed the cosmos with both the raw materials and the weird physics that make the universe interesting. Supernovae and the creation of heavy elements. A massive star that runs out of fuel can end its life in a huge explosion, and that explosion is where many of the elements heavier than iron are made. Stars slowly fuse lighter atoms, like hydrogen into helium, helium into carbon, and that process builds up layers inside the star, but it stalls at iron because making heavier elements by ordinary fusion would use up energy instead of releasing it. When the core collapses and the outer layers are blown apart, conditions become extreme enough for a different kind of chemistry to happen. Atomic nuclei pick up extra neutrons very quickly, one after another, and then some of those neutrons turn into protons, creating new, heavier elements. This fast chain of neutron captures happens so quickly that nuclei can climb to very heavy forms before they fall apart, which is why elements such as gold, platinum, and uranium can exist at all. Inside that explosion there is a chaotic, high-speed environment. Temperatures and pressures spike, and a flood of neutrons sweeps through existing atoms. Think of it like a sudden, energetic hailstorm of tiny particles that stick to atomic seeds and build them into something bigger. Tiny particles called neutrinos also stream out and can push and shake material in ways that help make and eject these heavy atoms. The result is a spray of newly forged elements, hurled into space at thousands of kilometers per second, mixing with surrounding gas and dust. Those blasted-out elements don't just vanish. They join the interstellar medium, the raw material for new stars, planets, and ultimately life. The gold in a wedding ring, the iodine in table salt supplements, the platinum in a catalytic converter, and uranium used in power all began as products of stellar processes, many traced back to explosive events like supernovae or collisions between compact stars. Your cell phone's tiny gold connectors were once part of a star's interior. That's both romantic and mildly inconvenient if you're allergic to space dust. Scientists today know that supernovae are major forgers of heavy elements, though they also understand that other cosmic events, such as collisions of dense dead stars, contribute as well. Different explosions and environments favor making different sets of elements, so the chemical richness of our world is the combined result of many stellar factories. So next time you hold a piece of metal or reach for a medicine, remember that ordinary things on Earth have an extraordinary origin. They are the leftovers of stellar tantrums, mixed into new creations and passed down to us, stardust with a good resume. Cosmic fireworks, supernova diversity and classification. Stars end their lives in a variety of powerful explosions, and astronomers sort these out by the light they emit and the chemical fingerprints left in that light. When a star explodes, it shines with a distinctive pattern. Some explosions show strong traces of hydrogen, while others do not, so scientists group them mainly by those visible clues. The way the brightness changes over time is another key clue. Some blasts fade quickly, others hold steady like a stubborn candle. One broad split puts explosions into two camps, those that show hydrogen and those that don't. Explosions that show hydrogen lines usually come from very big stars that run out of the fuel that keeps their cores puffed up. The core collapses and the outer layers are flung off. Think of it like a very tall sandcastle whose base suddenly gives way and the whole tower collapses outward. The other main group lacks hydrogen in their light and often comes from a small, dense star in a close pair that gathers extra material until it ignites all at once, more like adding too much batter to a tiny cake tin until it bursts through the oven. Within those two camps there are many flavors. Some hydrogen-rich explosions hold their brightness for a long stretch after the peak output. Astronomers call that a plateau, and it's like a campfire that keeps glowing at the same level for a while. Others fade more steadily and smoothly, more like the simple burn of a taper candle. Explosions labeled I-in show narrow lines in their light because the blast is slamming into a thick cloud of gas the star threw off earlier, producing extra glow. Picture a car splashing through a muddy puddle and throwing up a dramatic spray. On the hydrogen-poor side, there are kinds that still show helium and kinds that show almost nothing from the outer layers, because stellar winds or a companion star peeled those layers away beforehand. That's like removing the rind from an orange before squeezing it. A special subtype used for practical work is the thermonuclear explosion of a small, dense star that reaches instability in a binary partnership. These events tend to be surprisingly consistent in brightness, which makes them useful as distance markers across space. Astronomers use them to judge how far away galaxies are, much like judging distance by how bright a street lamp appears at night. There are also particularly bright outliers that shine far more intensely than typical explosions. Some of these may get an extra energy injection from a rapidly spinning, highly magnetized dense core left behind, which is a bit like a turbo booster attached to the wreckage. Classifying these cosmic explosions matters for more than cataloging. The type of explosion tells us what kind of star lived there, how elements heavier than helium are forged and scattered, and whether the leftover core became a dense neutron object or a black hole. In everyday terms, supernovae are the universe's way of sprinkling ingredients, iron, oxygen, calcium, into space soil so new stars and planets can form. Without them, we wouldn't have the material for rocky worlds or the iron in your kitchen pan. And for those who like a little cosmic humor, astronomers sort supernovae much like people at a fireworks stand. Some are Roman candles, some are sparklers, and a few are the wild, giant aerial bursts that everyone points at and says, wow. Observing supernovae, telescopes, surveys, and citizen science. A supernova shows up as a sudden, dramatic burst of light from a star, sometimes becoming brighter than everything around it for a little while. Telescopes collect that light and turn it into useful pictures or measurements. Optical telescopes capture visible light like a camera, radio telescopes listen to long, invisible waves the eye can't see, and 10th-ray telescopes pick up very energetic light that tells us about violent processes. Big professional observatories with large mirrors gather faint light from distant explosions, while smaller backyard scopes can still catch closer, brighter events. Think of a telescope as either a powerful pair of binoculars for deep space or a magnifying glass at a picnic. Both help, but one sees much farther. Large surveys scan the sky repeatedly to spot anything new or changing, working like a row of security cameras keeping watch over the heavens. These surveys use wide-field telescopes and automated software to compare fresh images to older ones, and that simple trick, image subtraction, where the old picture is removed from the new to reveal differences, is how many supernova candidates are first found. Real projects that do this include systems with names like Pan-STARRS, ZTF, and OSIS-SN, which are designed to cover large areas quickly instead of focusing on one tiny patch. The process is a lot like checking a photo album. If a new face shows up, you notice it right away. Enthusiastic volunteers on websites make a surprisingly large contribution by helping to filter through candidates that machines flag but humans must inspect. Platforms such as Zooniverse have citizen science projects where people mark likely supernovae from image pairs, and groups of amateur astronomers coordinated through organizations like the AAVSO can provide follow-up images with their own telescopes. That human touch, someone eyeballing a blink of light on a screen, is often quicker at weeding out glitches or known objects than an algorithm alone. It's a bit like a neighborhood watch where folks with ordinary cameras call out something unusual. Sometimes they're the first to report it. Catching a bright spot is only the beginning. Scientists then use follow-up instruments to learn what kind of explosion occurred and what it can tell us. One common tool is spectroscopy, which spreads the light into a rainbow so researchers can read chemical fingerprints, much like a chef tasting soup to figure out the ingredients. From those fingerprints we can tell whether the blast came from a white dwarf star that exploded in a particular way or from a massive star that collapsed under its own weight. Other telescopes look in radio or 10th rays to trace fast-moving material and shock waves, revealing details that visible light alone can't show. Practical steps for getting involved are straightforward and down-to-earth. Join a citizen science project online or connect with a local astronomy club. Practice taking and processing images with a small telescope or even a DSLR camera on a tripod, and learn simple image comparison techniques to spot newcomers. Report useful observations through community channels used by professionals and amateurs alike, and be ready to collaborate. Telescopes around the world often follow up the same target. And don't worry about competing with big observatories. Lots of discoveries start with a curious person, a modest setup, and a good cup of coffee. Famous supernovae in history and culture. Chinese court astronomers marked a suddenly bright, guest star that stayed visible for weeks. That event left behind what we now call the Crab Nebula, a glowing cloud of gas and a compact, spinning core, basically the cosmic equivalent of a leftover that still winks at you. Another supernova, recorded around the year 1006, was the brightest sight in the sky in living memory and startled observers from Asia to Europe. People compared its brightness to the moon. These explosions were not just bright lights, they left physical evidence that modern telescopes can point to and study, tying ancient notes in ink to objects we can photograph today. When a new star flared in Europe in 1572, Tycho Brahe wrote detailed observations that helped change how scholars thought about the heavens. People argued about whether the sky was unchanging and perfect, and that debate carried real cultural weight. Theology, philosophy, and science all tangled together. Kepler later examined another bright newcomer in our galaxy and used it in his own work. Poets and pamphleteers of the time treated these events as portents, and artists sketched them into celestial maps as though planning new constellations. In ordinary terms, a sudden star felt like a surprise billboard in the night sky and forced everyone to update their mental map. A much more recent and close supernova, observed in 1987, arrived at a moment when scientists had better tools and even detectors for elusive particles. Instruments on Earth picked up a brief burst of almost invisible messenger particles, confirming ideas about what happens when a massive star ends its life. Those particles, tiny and ghost-like, passed through rock and metal and still left traces that people could read, like fingerprints after a very fast handshake. The images from space telescopes of the expanding debris turned into icons used in classrooms, museums, and science articles, and they gave artists and documentarians vivid new material to work with. Astronomers got excited in a very human way. They compared notes, traded pictures, and felt like kids given new paint. Across cultures, bright new stars showed up in chronicles, poems, and even oral stories. Chinese court records are famous for their precision and give modern researchers timelines and descriptions that help identify which remnants match which ancient sighting. Islamic and Japanese scholars noted guest stars too, and European chroniclers often linked the events to political or religious meaning. Some researchers point to North American rock art and native stories that might reflect these flashes, though those links are debated and hard to prove. It's like trying to match a family photo to a story told around a campfire generations later. In modern popular culture, supernovae serve as metaphors for sudden transformation, dramatic endings, and new beginnings. Writers and filmmakers borrow the image of a star that dies brilliantly and leaves behind something unexpected. Museums exhibit Hubble or ground-based images, and schools use them to teach how observation and record-keeping across centuries form a chain from ancient skywatchers to today's scientists. The takeaway is simple and a little comforting. These cosmic fireworks have always been part science and part story, changing not only what we know about the universe but also how people make sense of dramatic change, like a loud drum roll for the cosmos, with a touch of stardust humor. Supernovae as distance markers, measuring the universe. Some exploding stars reach almost the same peak brightness when they blow apart, and that predictability is what makes them useful as cosmic measuring sticks. Astronomers call objects with known true brightness standard candles, which is a fancy way of saying they are like light bulbs of known wattage. If you know how bright the bulb really is and you see it dimmer from far away, you can figure out how far away it must be. The basic idea relies on a simple rule: light spreads out as it travels, so the farther you are, the dimmer the light looks. Think of a flashlight beam getting faint the more steps you take back. Measure how bright the supernova appears, compare that to how bright it should be, and you get the distance. Type Ia supernovae are the most commonly used of these reliable beacons, because the explosions come from a very similar process in similar stars, which makes their peak brightness fairly uniform. In plain terms, one star is quietly siphoning gas from a companion until it suddenly runs out of stable options and detonates. The details of that detonation tend to produce a predictable amount of light. Astronomers don't just take the peak brightness at face value though, they watch how the light rises and falls, a pattern called the light curve, and use that pattern to fine-tune the brightness estimate. It's like baking the same cake. If every oven behaves a bit differently, you might time it or check the texture to know whether it came out right. Redshift measurements complement the brightness trick, offering another angle on distance. Light that travels from faraway galaxies gets stretched as space itself expands, shifting its color toward the red end of the spectrum. This is much like the Doppler effect that makes a passing ambulance siren drop in pitch. By measuring that stretch and comparing it with the distance from the supernova's brightness, astronomers can chart how fast the universe is expanding at different places. Putting many such measurements together creates a map of cosmic expansion, and that map has led to major questions about a mysterious cause of accelerated expansion that scientists call dark energy, basically a placeholder name for something we know is influencing the universe but don't yet fully understand. Practical work with supernovae involves a lot of careful correction and timing. Dust between stars can make a supernova look redder and dimmer, so observers correct for that effect much like wiping a foggy window before judging a distant streetlight. Some supernovae occur in galaxies with properties that subtly change their light, so astronomers compare many examples and use color and spectral fingerprints to adjust their estimates. Telescopes and wide-field surveys try to catch these events early, because a supernova's brightness changes quickly and you want to measure the peak accurately. Missing the peak is like showing up to a fireworks show after the big bursts. Despite all that effort and the small uncertainties that remain, these exploding stars are among the best tools we have for measuring vast cosmic distances and for testing ideas about how the whole universe behaves. Superluminous and exotic explosions. Some stellar explosions can shine far brighter than ordinary ones, briefly becoming the brightest thing in their whole galaxy. These explosions are not just louder, they follow unusual rules, last longer, or put out energy in odd ways that ordinary supernovae do not. Observers note two broad flavors, those that show hydrogen in their light and those that do not, which tells astronomers whether the dying star still had its outer skin of hydrogen when it blew up. They are rare, and when they do appear they often come from small, actively star-forming galaxies that seem to favor the kinds of massive stars that make dramatic exits. One way to power these extreme fireworks is a central engine left behind after the star collapses, a tiny, ultra-dense star that spins very fast and has an enormous magnetic field. This object acts like a spinning dynamo, pouring energy into the expanding debris and making it glow much more brightly than it otherwise would. Think of a small, furious blender hidden inside a pillowcase, stirring and heating the whole mess from the inside. The pillowcase is the expanding stellar gas. Another common route to extra brightness is collision. If the star shed a lot of gas shortly before exploding, the blast runs into that gas and converts motion into light for us to see, much like a car hitting a snowbank and throwing up a spectacular spray of powder, messy and bright. Spectra that show narrow hydrogen features often point to this collision scenario, while spectra without hydrogen hint at engines or radioactive firepower. A truly exotic route comes from the strangest behavior in the cores of the most massive stars. When the core gets so hot that light itself can turn into matter and antimatter, the internal pressure suddenly drops. The star can then collapse and burn wildly, sometimes tearing itself apart in a single, complete explosion that leaves no compact remnant behind. In slightly less extreme cases the star undergoes a series of violent pulses, shedding shells of gas over time before a final, huge blast, like a pressure cooker that lets off steam in several loud bursts before finally blowing its lid. These pair instability processes can produce enormous amounts of radioactive elements that glow as they decay, fueling a bright, long-lived display much like embers that keep a bonfire glowing long after the flames have died down. Observers look for clues across the spectrum to tell which story unfolded. Slow, very bright light curves and broad spectral features can point to massive radioactive yields or sustained engine input, while bright 10th ray or radio emission often accompanies collisions with dense surrounding gas. There are also lookalikes. Some giant eruptions from very large stars can mimic a supernova without fully destroying the star, the astronomical version of a dramatic but non-fatal tantrum. Practically, these explosions serve as cosmic laboratories. They test how the most massive stars live and die, seed space with heavy elements, and act as beacons that help astronomers probe the distant universe. And yes, from a human point of view they are the universe's over-the-top fireworks, awe-inspiring, puzzling, and entertaining enough that even the cosmos occasionally goes for the dramatic close-up. Binary stars and explosive interactions. Many stars live in pairs, locked in orbits around one another, and those relationships change everything about how they end their lives. When the stars are close enough, one can steal gas from the other, slowly piling material onto its partner like pouring syrup onto a pancake. That steady transfer can be gentle at first, causing small surface flashes, or it can push a compact star to a breaking point and trigger a catastrophic explosion. A common scene involves a dense, Earth-sized remnant called a white dwarf drawing gas off a nearby companion. The gas forms a thin, hot layer that occasionally flashes in surface eruptions known as novae. Think of a pressure cooker releasing steam. If the white dwarf keeps gaining mass, it can cross a stability limit and suffer a thermonuclear runaway, a single, powerful blast that blows the star apart. This is the kind of supernova used by astronomers as a reliable yardstick for distance. The process that moves gas from one star to another often happens because the donor star overflows an imaginary boundary of control. Astronomers call that overflow a Roche-Lobe transfer, but you can picture it as a cup filling until it spills over into the neighbor's lap. Pairs of dead stars can also merge. Two white dwarfs spiraling together will heat up and, when they finally collide, may ignite a gigantic thermonuclear explosion. That is different from the single-star case because both partners are compact and have no big envelopes of hydrogen left. In other systems, a massive star can be stripped of its outer layers by a companion before collapsing. Losing that outer skin changes the look of the resulting explosion. Stripped stars give off supernovae that lack the usual hydrogen signatures, a bit like removing an outer coat before stepping outside in winter. The end result is colder in one way and different in another. Sometimes the interaction gets messy and fast. If one star expands and engulfs its partner, both can end up inside a shared envelope of gas. Friction inside that envelope pulls the two cores closer together, and the envelope can be flung off into space. This so-called common envelope phase tightens the binary and can set the stage for later fireworks. Close pairs of neutron stars or white dwarfs may eventually merge and produce bright explosions or even ripples in spacetime. Think of it as an awkward dance where someone steps on a dress and both partners end up much closer than they started. The practical upshot is that binary interactions create a rich variety of explosive endings. They explain why some supernovae shine with certain elements while others do not, and why some are sudden flashes from an aged compact star while others follow a violent merger. Everyday comparisons help. Mass transfer is like overflowing a cup, envelope stripping like peeling an onion, and mergers like two soap bubbles joining then popping, messy, quick, and dramatic. Astronomers study these stellar relationships to understand how elements get spread into space, how compact object pairs form, and how different types of cosmic fireworks are produced, which in turn helps explain the material we find on planets and in our own bodies. The role of supernovae in galaxy evolution. Supernovae are the main factories that make and spread the heavier elements in galaxies, tossing out oxygen, carbon, iron and other building blocks that planets and living things need. These explosions take place inside the gas between stars. Think of that gas as a thin cosmic soup, and they mix new ingredients into it so future stars and planets form from richer material. For example, the iron in your blood and the calcium in your bones were forged in past generations of stars and then flung into space by violent stellar deaths. It's a neat way to say we are literal stardust, and a little funny to think about when you misplace your keys. When a big star explodes, it sends a shock wave through surrounding gas, and that wave acts like a cosmic plow, compressing pockets of gas so they can collapse into new stars. Sometimes the blast nudges a quiet cloud into making babies. Short sentence. Other times it heats and stirs the gas so much that star formation slows down, because warm, turbulent gas resists collapse. This push and pull is called feedback, and it works like a thermostat for a galaxy. Too many supernovae can shut down star formation for a while, too few and the galaxy can keep forming stars without pause. Many explosions together create winds that can sweep gas out of a galaxy or lift it into a surrounding halo, carrying metals far from where they were born. This matters because it sets where new stars will be born and how metal-rich different parts of a galaxy become. Inner regions tend to be richer in heavy elements than the outskirts, largely because supernovae keep enriching the central gas repeatedly. Picture a city where factories both supply stores with goods and send trash out to the suburbs. Supernovae are those factories, supplying materials but also moving stuff around. Supernova-driven turbulence and cosmic rays change the temperature and chemistry of the gas, affecting how clouds cool and stick together. Cosmic rays are fast particles accelerated by explosion fronts, and although that sounds like sci-fi, their effect is simple. They help ionize gas and sometimes push on it, aiding the creation of galactic winds. Collective explosions in star clusters can carve superbubbles, large cavities in the gas layer, that punch holes upward like chimneys, allowing hot gas and metals to escape into the galaxy's outer regions. Small galaxies feel this more strongly. A strong series of blasts can remove a lot of gas and leave the galaxy with little fuel for new stars. Dust survives and is also processed by supernovae, which both create and destroy tiny solid grains. These grains are crucial because they help gas cool and stick, and they act as the seeds for planet formation. A dusty mix is needed to make rocky worlds. In short, supernovae reshape the material budget of galaxies. They create key elements, move them around, regulate when and where stars form, and influence the large-scale structure of gas. The result is a galaxy that keeps evolving, shaped in large part by the dramatic endings of its most massive stars. sometimes nurturing new life, sometimes blowing the whistle and calling a timeout. Simulations and models, recreating stellar explosions. Astrophysicists build detailed computer models to replay how massive stars blow apart at the end of their lives, turning complex physics into numbers that can be watched, tweaked, and compared with telescope data. These virtual explosions help connect theoretical ideas to real signals, like how bright a supernova gets over time, the colors of its light, and which chemical elements get flung into space. Think of it as a laboratory where the experiment is too big to bring into the classroom, so you recreate it with a very clever set of simulations instead. One common approach is to start with simpler, one-dimensional models that track how conditions change from a star's center to its surface, and then add more realism with two- and three-dimensional runs that capture asymmetry and turbulence. Simple models are useful for testing ideas quickly, but full 3D simulations are needed to see how chaotic flows and instabilities actually shape an explosion. Code such as MESA are often used to evolve a star up to the point of collapse, while hydrodynamics tools like Flash or Castro handle the violent fluid motions. Specialized packages like Chimera and Fornax include detailed treatment of neutrinos, which are crucial for core collapse events. Each code has strengths, and researchers pick the right tool or combine several to answer a specific question. The ingredients inside these models are many and sometimes counterintuitive: fluid flow, how stellar material moves; nuclear reactions, how atoms fuse or break apart and release energy; neutrino transport, how nearly invisible particles carry energy away; magnetic fields, and rotation. Fluid flow can be likened to boiling water in a pot. Hotter material rises and cooler material sinks, while turbulent mixing behaves like stirring paint, creating swirls and filaments. Nuclear reactions act like tiny fireworks inside the star, producing heat and new elements. Neutrinos behave like a draft under a door, letting energy slip out almost unnoticed but with big consequences for whether the star explodes or not. To make those ingredients behave realistically, simulations use techniques such as adaptive mesh refinement, or AMR, which concentrates computing effort where things change fastest. Picture zooming in on the frothiest part of a boiling pot and leaving the calm surface less detailed. High-performance computing is essential because resolving small turbulent eddies alongside the entire star demands huge computational power. Scientists run these models on supercomputers using thousands of processors or on newer graphics processors that speed up the math. Nuclear reaction networks are included to follow how different elements form, and microphysics tables tell the code how matter behaves at extreme densities and temperatures. The results are then compared with observations: the shape of the observed light curve, the spectrum of the light which reveals chemical fingerprints, and the morphology of supernova remnants seen in telescopes. Despite steady progress, there are real challenges that keep scientists busy. The range of scales, from tiny turbulence to the size of a star, puts enormous demands on resolution and computing time. Some pieces of the physics, such as the detailed ways neutrinos interact with dense matter or the exact behavior of matter under extreme pressure, remain uncertain and are treated with carefully tested approximations. Researchers cope by running many simulations with slightly different assumptions and looking for robust trends, much like a chef tweaking a recipe several times until the dish comes out right. The payoff is practical and immediate. Better models help observers decode telescope data, reveal how elements like iron and gold are forged, and guide future observations with clearer predictions. A little humor helps maintain sanity too. Some runs fail spectacularly, and calling that an explosion of learning is almost literal. Risks and myths. Are supernovae dangerous to Earth? Supernovae are massive stellar explosions that release enormous amounts of energy into space, and that energy can travel as particles and high-energy light. In simple terms, think of a supernova as a star suddenly blowing its horn at full volume across the galaxy. The sound here is light and particles, not something you could hear. The immediate radiation from a distant supernova simply washes past Earth harmlessly because our atmosphere and magnetic field act like a thick coat and a strong umbrella. On the other hand, if such an explosion happened unusually close in cosmic terms, the effects could be more than a bright light show. The main risks scientists consider are increased radiation reaching the atmosphere and the possible thinning of the ozone layer, which protects us from the sun's harmful ultraviolet light. Picture the ozone as Earth's sunscreen. If it gets rubbed off a bit, more UV reaches the surface and living things can get sunburned or have trouble reproducing. Small organisms near the base of the food chain, such as ocean plankton, would be most vulnerable. That matters because when the tiny guys suffer, the whole food web can wobble like a table missing a leg. Not every supernova sprays Earth with dangerous stuff. The orientation, distance, and type of explosion all matter. Another concern sometimes mentioned is gamma-ray bursts, which are very focused jets of extremely energetic light that in rare cases accompany certain stellar collapses. If one of those jets were pointed straight at Earth and came from a relatively close star, it could do more damage than a typical supernova because the energy is concentrated like a cosmic laser pointer. Still, those events are exceptionally directional and rare, and the chance of Earth being directly in the line of such a jet is tiny. In other words, you're much more likely to lose your socks in the dryer than to be hit by a life-changing gamma-ray burst. There are real scientific clues that Earth has been nudged by nearby explosions in the past, such as traces of unusual isotopes found in deep-sea sediments, which are best explained by debris from exploded stars. That doesn't mean Armageddon followed though. It only says that our planet occasionally catches some cosmic fallout, like getting a few muddy drops from a passing car in a rainstorm. Scientists study these clues to learn how strong past effects were and how ecosystems responded, and the results suggest that while a nearby supernova could stress life, it's not an automatic extinction event that wipes everything out. Popular culture tends to exaggerate the threat, showing planets instantly vaporized or solar systems collapsing in dramatic CGI. Reality is more subtle. Distance and direction are everything, and the Earth's defenses are surprisingly effective. Practical risk today is low because no known star close enough and in the right condition is poised to deliver a dangerous blast toward us. So, while supernovae are awe-inspiring and can, under specific and uncommon circumstances, affect Earth's environment, they are not an everyday hazard to cancel your picnic plans. Future discoveries, next-generation observatories. New instruments will let astronomers see fainter flashes and finer details of exploding stars that were invisible before. Space telescopes that look in infrared light, like the one that peers past dust to find hidden heat, can spot the warm glow after an explosion and measure the cooldown, while giant ground telescopes with very large mirrors act like super-zoom cameras to pick out tiny features on a distant blast. Wide-field survey telescopes sweep large parts of the sky repeatedly, catching surprises quickly, and radio arrays listen to longer wavelength whispers from the debris. For example, an infrared observatory can reveal a shroud of dust forming around the debris, and a big optical telescope can then take a close-up spectrum, the rainbow-like fingerprint that tells what elements are present. It's a bit like having a high-end DSLR, a wide-angle action cam, and a stethoscope all pointing at the same fireworks show. Catching the very first light of an explosion is one of the biggest practical gains. Some telescopes are designed to scan the sky every night and alert other instruments within minutes, so follow-up observations can start before the glow fades. Early spectra can show how fast the outer layers are moving and what they're made of, and that helps decide whether the exploding star was a hefty giant or a smaller companion that went boom after stealing material. Think of it as getting the first frame of a video instead of only seeing the aftermath. Scientists can then rewind and model the sequence more reliably. And when instruments cover different colors of light, from radio to infrared to 10th rays, they reveal separate pieces of the story, like hearing the crackle of a campfire and smelling the smoke. Coordinated observations with non-light detectors add another layer of insight. Gravitational wave observatories provide the rumble that can signal a violent merger or collapse, and big neutrino detectors pick up ghostly particles that escape from the dense core before the light brightens. When those signals are combined with optical, infrared, radio, and 10th ray data, researchers can put together the who-did-what timeline of the explosion. A good analogy is a crime scene investigation where you have security camera footage, eyewitness accounts, and fingerprints. Each type of evidence rules out different suspects. Robotic telescopes and automatic alert systems help by making sure no crucial moment is missed, because in astrophysics, timing is often everything. The practical outcomes will touch many questions: how different kinds of stars end their lives, how elements like iron and calcium are forged and spread, and how explosions affect their galactic neighborhoods. Better observations refine the models that predict brightness and behavior, which in turn improve methods for measuring cosmic distances, useful for mapping the universe. Everyday examples help make this less abstract. Understanding how supernovae make elements is like learning which kitchen process produces a certain flavor in a dish. Knowing the recipe matters if you want to reproduce it. And yes, astronomers will likely be surprised now and then. New instruments have a habit of turning "that can't be" into "oh, that's interesting." Bringing it together: why supernovae matter. Supernovae scatter the elements forged inside stars out into space, and that simple fact explains much of their importance. Elements like carbon, oxygen, iron, and even heavier ones such as gold are produced in stars and released during these powerful explosions, seeding the clouds of gas and dust that will one day form new stars and planets. Think of it as a cosmic kitchen. A star cooks up elements, then dumps them into the pantry when it blows apart, and future recipes, planets, moons, and eventually life, use those ingredients. The iron in your blood and the calcium in your bones both owe their existence to this process, so these explosions are literally part of the story of life on Earth. Some supernovae act as reliable distance markers for astronomers. A particular kind tends to reach a similar peak brightness when it explodes, which lets scientists compare how bright it appears from Earth and infer how far away it must be. That ability to gauge distance is crucial when mapping the universe and understanding how galaxies are spread out. Without these cosmic mileposts, astronomers would struggle to measure the scale of the cosmos, and many ideas about how fast the universe expands would be much harder to test. It's like using identical streetlights to figure out how far down the road you're looking. Beyond supplying raw materials and serving as measuring tools, supernova explosions reshape their surroundings. The blast sends out shock waves that compress nearby clouds of gas, sometimes nudging them into forming new stars. In this way, supernovae help drive the cycle of birth and rebirth in galaxies. Picture a gardener tossing compost onto a flower bed, messy, noisy, and a little dramatic, but ultimately productive. The same messy drama applies on cosmic scales. Destruction leads to creation. High-energy particles produced by supernovae, called cosmic rays, are another practical consequence. These particles zip through space and can affect electronics on spacecraft, so engineers take them into account when designing satellites and instruments. Astronauts and high-flying aircraft also face slightly higher background radiation, which is considered in safety planning. And on a more philosophical level, supernovae connect the everyday to the extraordinary: the gold in a wedding band, the iodine in table salt, the oxygen you breathe, all trace back to star explosions. So when you look at the night sky, you're seeing a landscape shaped by countless ancient blasts that made the ingredients and the rules for everything we know. So that's the complete story of supernovae in a nutshell. Some stars blow up because they run out of fuel and collapse under their own weight. Others explode when a buddy star donates too much, like borrowing sugar and setting off a kitchen disaster. Those explosions light up the sky like giant fireworks, leave behind strange, tiny cities of superdense matter, neutron stars, or invisible gravity traps, black holes, and fling the heavy elements that make planets, phones, and even you across the galaxy. Think of it as cosmic recycling. Stars die, their guts spread out, and new stars and worlds are born, like compost for the universe, but much flashier. If any of this surprised you, you're not alone. These explosions are both violent and beautiful, and they quietly made the stuff in your jewelry and your bones. Thanks for watching and going on this trip from a single spark to a sky-wide boom with me. If you enjoyed the journey, like the video, subscribe for more space stories, and tell me in the comments which moment blew your mind the most, or which analogy made you laugh. Next time we'll zoom in on famous supernova leftovers like the Crab Nebula, show how telescopes catch these blasts, and follow the trail from exploding star to the gold in your favorite ring. See you in the next video. Bring curiosity and maybe some popcorn.